Hello everyone and welcome back. If you have reached this specific video, then that means you have already started attempting Physics AS level past papers, specifically Paper 2, Variant 2 of the May-June 2023 series. Moreover, you might have already gone through all of questions 1, 2, 3 and 4. We already have dedicated videos we've already uploaded to this channel. So, if you haven't attempted them yet, I would highly encourage you to check those out first before we dive into question 5. So, if you're done with those, then let us begin. Here we have question 5a. A progressive wave travels through a medium. The wave causes a particle of the medium to vibrate along a line P. The energy of the wave propagates along a line Q. Compare the directions of lines P and Q if the wave is a transverse wave and then a longitudinal wave. Let's suppose that particle is this red dot that I'm drawing. The energy of the wave is propagating along a line Q, which is the same as the direction of the wave itself. So let's call it the wave direction. Since they haven't really specified where it's going, let's choose the simplest one, which is a wave moving from left to right. Now, if for a transverse wave, we know that the particle has to move in a transverse direction, meaning in a direction that's perpendicular to the wave direction. In this case, that would be vertical. So the bottom line is that P and Q for a transverse wave happen to be perpendicular to each other. For a longitudinal wave, the scenario is the opposite. For a wave that's moving from left to right, as I show in Q, for a longitudinal wave, the particle wouldn't move up and down but rather sideways, which means that now P and Q, instead of being perpendicular, are now parallel, specifically for a longitudinal wave, right? Let's move to the next question. A tube is closed at one end. A loudspeaker is placed near the other end of the tube as shown in figure 5.1. The loudspeaker emits sound of frequency 1.7 kHz. The speed of sound in the air in the tube is 340 meters per second. A stationary wave is formed with an antinode A at the open end of the tube, and there is only one other antinode A inside the tube as shown in figure 5.1. The first part says to determine the wavelength of the sound. Now, here if we look back at the question, we are already given the frequency and the speed of sound in air. Let's note them down over here. So the frequency is 1.7 kHz, which we can multiply by 1000 to get rid of the kilo, and we get 1.7 into 10 raised to the power 3 Hz. For wave speed, that's a straightforward 340 meters per second. And now we just have to figure out the wavelength lambda. There's only one formula that links wavelength frequency and the wave speed, which is wave speed equals frequency times wavelength, except this time we'll be making wavelength the subject of the formula. For that, all I'll have to do is divide both sides by frequency, and that gives me wave speed over frequency. So we get 340 over 1.7 into 10 raised to the power 3, and that should give you 0.2 meters approximately. And so that's our wavelength. Alright, great. Now to the next part. We have to figure out the length L of the tube. For this, we have to refresh a little bit of our knowledge about stationary waves. We know that stationary waves comprise of loops that look something like this. Here I'm drawing it a bit roughly, not related to this particular question. For these kinds of loops, we know that they comprise of these crossed points that I'm dotting right now. These are basically points where there are no displacements occurring for the particle, and those are what we call nodes labeled N. In between consecutive nodes, you have this region or this point where particles exhibit maximum displacement, and those we call antinodes. You can think of antinodes as the opposite of nodes. Where nodes don't undergo any displacement, antinodes undergo the most displacement, right? Hence the name antinode. Now over here we are told the positions for the two antinodes, meaning in between two antinodes there will definitely be a node, and there will also be a node at the closed end, which makes physical sense. Why? Because if you think about it, a particle at the closed end won't be really allowed to displace anywhere, so there is no displacement there. So just for the sake of being able to visualize stationary waves, it always helps to draw these kinds of loops. Even if you don't expect them to be there physically, it helps to at least make the question easier to solve. And you'll see that in just a moment. So let's sketch our stationary wave here. So that's 1, So that's one loop here, made from one line, and then comes the other, right? So here we have one loop, and then we have half a loop. So in total, how many loops do we have? Well, we have 3 over 2 loops, or you could also say 1.5 loops. It's the same thing. Now, why are we counting the loops? Because we want to relate the number of loops with the length L of the tube. For that, there's another property we can use about stationary waves. That one loop meaning one. So, okay, here let me actually take a pause and mention one thing. That when I say one loop, I basically mean the distance, basically 2 consecutive nodes or antinodes. It's easier to locate the nodes, so let's just focus there. So 2 consecutive nodes. Now, for that one loop and for the distance between 2 consecutive nodes, the distance is equal to half a wavelength. So if you have for one loop half a wavelength worth of a distance, then for half of that loop, it would just be a further half of the distance lambda over 2, which would give you lambda over 4, right? So it turns out that the length L happens to be equal to lambda over 2 plus lambda over 4, right? So you have to combine them. So L is equal to lambda over 4, which is coming from half of the loop. And then lambda over 2 comes from one whole loop, which will equal 3 lambda over 4. So now it's just a matter of plugging everything in. 3 times 0.2 over 4. And we should get approximately 0.15 meters. Right? Alright, let's go to the next part. The maximum wavelength of the sound from the speaker that can produce a stationary wave in the tube. The largest wavelength that you can get won't be for these many loops, because the arrangement because the more loops you start fitting in the same length L, the smaller those loops get, right? Imagine if I tried to fit in 3 loops inside, then I'd have something like this. So clearly you can see how the loops are getting smaller and smaller, which would lead to an even smaller wavelength. So instead what you want is basically the largest, you basically want to fit in the least amount of loops inside. We want to fit in the least amount of loops. That way you can expect those loops to spread over the tube a lot more, hence giving you a larger wavelength. And there is only one kind of arrangement that can give you the least amount of loops. That's basically the arrangement of the stationary wave that you draw for the fundamental frequency. You might recall that the fundamental frequency refers to the frequency of that wavelength, of that stationary wave that you can fit in, which is basically the smallest number of loops that you can fit inside a tube, right? So for a tube like we have, which is open at one end and closed at the other, the simplest arrangement that we can have that can be related to the fundamental frequency would be one where you have a node over here and an antinode at the open end, and then nothing else in between, which would mean you have half a loop basically. So now what you've established is that the length L of the tube, which we already know, is equal to lambda over 2, which is for one loop, divided by half, which is lambda over 4. Therefore, that maximum wavelength is 4 times the length L, which would be 4 times 0.15. And let's see, what do we get? We'll get exactly 0.6 meters. So that's your maximum wavelength that you could possibly fit inside the tube, right? Now let's move to the next question, or the next part rather. 2 polarizing filters are arranged so that their planes are vertical and parallel. The first filter has its transmission axis at an angle of 35 degrees to the vertical, and the second filter has its transmission axis at angle alpha to the vertical as shown in figure 5.2. Angle alpha is greater than 35 degrees and less than 90 degrees. A beam of vertically polarized light of intensity 8.5 watt per meter square is incident normally on the first filter. Now let's move to the first part. show that the intensity of the light transmitted by the first filter is 5.7 watt per meter square. Now this is quite straightforward because we know there's a formula that relates the incoming intensity, I'll call that I naught, with the outgoing intensity, I'll call that just I. And we can relate it with this angle between the vertical axis and the transmission axis. Let's call that angle theta. The formula that relates these three quantities is basically that the outgoing intensity I is basically the ingoing intensity I naught times cos square theta, where theta is that angle between the vertical axis and the transmission axis. So now it's just a matter of plugging everything in. So you have 8.5 I naught as I naught, and then theta is 35. So it's 8.5 times cos 35 whole squared. And let's see what do we get on our calculator. So cos 35 whole square gives you 0.671, and this you multiply with 8.5 and you'll get 5.704. So even if it's not an exact 5.7, it does round off to 5.7 when you round it off to the nearest or the next first two significant figures, watt per meter square. Right? So you have successfully proven this. Alright, let's move to the last part. The intensity of the light transmitted by the second filter is 5.2 watt per meter square. Calculate angle alpha. Now if you go back here, to calculate this unknown angle alpha, we have to first understand how the light itself has been polarized and in what direction after every filter is passing through. Firstly, it was entering in a vertically polarized manner. So let's say that arrow, let's actually draw that arrow with a different color. Let's draw it with purple, like so. So that was the vertically polarized light at the beginning. After having passed through the first filter, which is tilted at an angle of 35 degrees, then it in itself has tilted in a 35-degree angle. That's something that must be known. So it's not really vertical anymore. It has a different intensity, yes, but at the same time, it's not vertical anymore, but rather itself is tilted at 35 degrees. So let's mention that over here. So that now, after having this 35-degree tilt, it's going to encounter the second filter like this. So let me draw that here to make it more apparent. So over here, with that further tilt of alpha, which is greater than 35, that this intensity of light I is going to enter here like so. Let me draw it a bit more carefully. So this purple line that I've drawn is the incident light ray I, and the new light ray that's going to come out is going to be arranged in this new axis. Now notice how this angle isn't really alpha anymore. Let me draw this separately to make it a bit more clear. So that's your vertical axis, right? Then you have your 35-degree incident light coming from the first filter. And then you have the new, let me label it I. And then you have the new light ray that's going to come out from here. Let's call that I1. So it's going to be the new one, I1, with that new intensity of 5.2 watt per meter square. Now, I might be inclined to use just the formula directly, that the outgoing intensity is equal to the incoming intensity times a factor of cos square with alpha over here. But we can't really do that here because the angle that you in place here should be the angle that's between both the incident and the outgoing light rays. It's not really going to be alpha in this case. Let's call this new angle, whatever this angle is, it's going to add up to the 35 degree to give you the total alpha. So the angle alpha is going to be 35 degrees, which is the original tilt of the incoming intensity of light coming from the first filter, plus the additional tilt that's coming after the light ray has passed through the second filter. Let's call this angle beta. So our job is to first find beta, and from that value of beta, we'll be able to calculate what alpha will be, right? So our formula won't be cos square alpha, but rather will be cos square beta. Because I repeat, the formula requires an angle theta, yes, but that angle theta has to be the angle between the incoming light ray, it has to be the angle between the polarization of the incoming light ray and the polarization of the outgoing light ray, which in this case I've labeled as beta. So it's this in-between angle. So now let's go back here and use that formula first to figure out what beta is. That I1 equals to I cos square beta and not alpha. Again, our job is to first find what beta is. I1 is the final outgoing intensity, 5.2. I is the initial ingoing intensity after having passed through the first filters, that's 5.7. Cos square beta. Dividing 5.7 on both sides, I get this. I can take a square root on both sides to get rid of the square factor. I get cos beta equals 5.2 over 5.7 square root. And then it's just a matter of taking the inverse on both sides. I don't have to worry too much about solving this step by step every time. What matters is the final answer. And once you plug everything in and evaluate this at the end, you will get 17.2 degrees. That 17.2 degrees you'll now add to that 35. And what you will get? 52.2 degrees, which you can round off to 52 degrees. So voila, that's your final answer. So not only have we discussed some important properties of waves and sound waves, and especially in the context of stationary waves, but we also discussed a little bit about polarization of light and how intensities change according to the angle tilt, right? So in our next video, we'll start off with question 6. Thank you for your time.